Next is similar to the plane wall, we can have a convective boundary condition. Means that this, if I draw this front view, that means in r theta plane, instead of prescribing the inner surface and outer surface temperature, we prescribe the fluid temperature, inner fluid temperature, which may be TFI, and outer fluid temperature, which may be TFO. That means the heat comes from the inner fluid to this. Let us consider TFI, fluid temperature inner, is greater than TFO. Then first by convection heat will come to the inner surface and it will have a temperature T1 which is not prescribed. And then heat will flow by conduction to this outer surface which will attain some temperature T2, and from T2 by convection it will go to outside fluid TFO. For example, heat is being lost from a hot fluid flowing through the pipe. So in that case, T1, if T1 and T2 are not prescribed, only TFI, TFO, then what we can do? We know that conduction heat transfer between T1, T2, if T1 and T2 are the inner and outer surface temperatures which may not be prescribed, but I take as this temperatures is denoted as T1, T2. I already know that this is equal to ln R2 by R1 divided by 2 pi Lk, and same heat Q is coming through because of steady state, the same heat is flowing by convection from the inner hot fluid to the surface, and if I prescribe Hi as the heat transfer coefficient of the inner fluid and HO that of the outer fluid, then by our definition of the heat transfer coefficient in convection heat transfer, D can be written as heat transfer coefficient into area twice pi R1L, inner surface area, into TFI minus T1. And that is same as that goes out from the outer surface to the outer fluid environment, which is taken to be cold here, less. Therefore, this will be twice pi R2L into T2 minus TF outer. So in the similar way as we did earlier, we can express this if T1, T2 Q times this, TF minus Ti is Q times this, Q divided by this, Q divided by this, and T2 minus TFO is Q divided by this, and if we sum it up, then we get Q is equal to, in terms of the extreme temperature difference which are prescribed, that is TFI minus TFO divided by 1 by 2 pi R1 H1 plus ln R2 by R3 divided by twice pi Lk R1L, sorry, twice pi, twice pi R1 L Hi plus 1 by twice pi R2 L H. Extremely simple. So it is the R1 and it is R2. ln R2 by R1. I have written R. Sorry, very good. Very good. Now, this is same as the flat plate thing. That means it is the sum of the three series resistance. This is convection resistance, C convection. Inner surface I, this is R conduction, and this is R convection outer surface. That means extremely simple. Three resistances are in parallel through which the same heat is flowing, and the electrical analogous circuit is like this, TFI and TFO. The same heat is flowing Q with, this is R convection, I whose value is 1 by 2 pi R1 LH1, and this is conduction, and this is R convection. Same thing. We can also think of composite cylinders or composite cylindrical walls which may be composed of different thermal conductivity. Then we will have the different conduction resistance in series. Different conduction resistance in series. So it will be nothing great. If we solve problems, then you will see the application of it. That means instead of one cylindrical wall, we may have a composite cylindrical wall. That means we have another cylindrical layer of material of different thermal conductivity. Then we will be adding another conduction resistance like this. That will be from R2 to R3. That means if we have another, just like this, I give you a picture like this, and this will be very simple to deduce. This will be very simple to deduce. This will be very simple to deduce like this. If we have two cylindrical walls, the radiuses are R1, R2 and R3. Then R1 to R2, this material has thermal this is A, thermal conductivity Ka, and this R2 to R3, this material is B with thermal conductivity Kb. And if we have the similar TFI and TFO with HO and HI, heat transfer coefficient, then your circuit will be the same with another added resistance, which will be very simple to conceive, and we can draw the network like this. One convective resistance, then two conduction resistance, and again a convective resistance. So that these two terminals are the extreme potentials. TFI, Q flows like this, TFI is greater than TFO, and we get this convection. What is that? 1 by twice pi R1 L HI. Then this is R conduction for material A, that is ln R2 by R1 outer to inner radius divided by twice pi L Ka. Similarly, this is R conduction B, which is ln R3 by R2 outer to inner radius of this cylindrical wall divided by twice pi L Kb, and this is finally R convection O, that is outer 1 by twice pi, this I write first, R3, the area L into HO. So this is so simple. So therefore, this is the thing. That means composite cylindrical wall with convective boundary conditions are tackled like that. How do we get this distribution? We solve the temperature distribution by developing a expression from the energy balance, that is the heat balance, energy balance in the conducting medium by taking a small elemental volume, or you can start with the general heat conduction equation as I have told, then you solve it for the special case. If there is heat generation, then heat generation term has to be taken its dependence with the spatial coordinates have to be taken. If thermal conductivity depends on temperature, then its dependence has to be taken. Then the problem becomes mathematical. That means whatever is involved is mathematics, so there is no other heat transfer concept. But one very important thing which sometimes many books forget to tell, that for a variable area, plane area problem, if you start from the general heat conduction equation, you will be lost. You have to develop that equation by taking that I told in the last class, the energy balance, because the concept of variable area is not there, because it is integrated over a cross section to get a mean temperature effect, or the temperature being uniform but area is varying. That part will not be manifested if you straightforward take from the heat conduction equation. This is a very general mistake in student days. I tell you, a teacher always tells his experience from student days. The students always jump to the general energy equation. He finds that okay, he makes steady state del T 0, he makes Q 0, he makes everything 0, then you get that d square T dx square 0, T has to be linear in x. Unfortunately, a one-dimensional heat conduction, this is an approximation of course, for a varying area, T is never linear. T is never linear. It is A into dt dx which is constant. So dt dx is inversely proportional to A. That concept has to be clear. But in cylindrical coordinate system, because of the coordinate system itself, the area, it is inherent within the coordinate system that the area normal to heat flow, for example in the r direction, is varying with r, it is directly proportional with r. So therefore, from the general heat conduction equation, if you take the special form, it will be same as you deduce by taking a simple element one-dimensional QR and QR plus del R like that. Both the things are same. I think for you people, these two things have to be kept in mind, otherwise you will be in trouble. That even in variable area, you will draw a linear temperature profile, then come to the teacher and tell why in a steady state one-dimensional constant thermal conductivity temperature is linear, why I have not got the mark. So this is very important. Okay. So today I will stop here. Well, it is little before the time, but the next thing is the critical thickness of insulation. That I will take in the next class. Now I tell you, just wait, I give you a clue now before starting the next topic, that when this heat flux is given by this, one thing you see, that if you increase the outer radius, then two things happen in contrasting nature. We increase the outer radius, the conduction resistance increases, but the convection resistance decreases. This is because surface area of heat transfer increases. You understand? Which is not the case for a plane area. If there is a heat transfer from a wall, if you go on adding material to increase the wall thickness in the direction of heat flow, you are sure that you are putting more conduction resistance and the heat flux will be arrested. That means it will be reduced, obviously, because your dt dx is getting reduced. But in a cylindrical geometry, if you increase the area, increase the radius by more material, that means you are increasing the radial path for conduction, and conduction resistance increase. But at the same time, mathematically, you see the convection resistance decreases. Means the surface area from which the convection heat transfer takes place increases, and convection is directly proportional to surface area. You understand me? So therefore, the two counteracting things results in a very interesting problem as critical thickness of insulation. That means if you insulate a cylindrical pipe by giving insulating material, adding insulating materials whose thermal conductivity is relatively much lower than the common conducting material, does not always mean that we are going to reduce the heat loss. Ironically, you will see that you are increasing the heat loss, because there are two contradicting things. Conduction resistance increase, but the convection resistance